Well, so here's the solution, right? You write down the vector, expand it and write it as a linear combination of vectors and the basis. That's going to be our answer, the vector ABC. So this equality means these two polynomials are the same polynomial. Therefore, the coefficients of 1, x, and x squared have to be the same. So if I sort of rewrite this to be a plus b times 1 plus c times x plus b times x squared, I can equate them left and right. The coefficient of 1, the coefficient of x, the coefficient of x squared, which is 0 on the left. So that leads me to 1 equals a plus b, 2 equals c, and 0 equals b. So I have the solution for the representation of this vector in this basis of the spaces 1, 0, 2. Okay, does that, you guys, okay? Now, the problem we're asked is this vector in the image of the map given in this space? So what we do is we take, let me copy the matrix J down here. This is part B, the actual problem is we have J taking you from the standard basis to D equals 1, 3, 0. I'm just copying the matrix down on the page. Okay. Now, what this does is this takes, okay, let me make this not an equality, but it is an equality, but I don't want to, okay, this is J. Now, it acts on a vector in R3C, but no, we can't use X, Y, and Z because in the polynomial space we have this X. We could, but let's just use R, S, and T. So it takes any vector in R3, and we want to know, is there a vector that has components R, S, and T to which this matrix multiplication equals this vector here, 1, 0, 2, right? Because if I can solve, this is a linear system. If I can solve this linear system, if I can solve, or let's make it the other way around. If you can solve this linear system for some R, S, and T, then W is in the range of the map J. Okay, so therefore, the first bit of this problem is discovering which linear system you have to solve, right? And so then we can immediately write down the augmented matrix for this. Minus row 1 plus row 3. 1, 3, 0, 1, and we're not going to change the second one, but we're going to do minus 1 times plus 1 is 0, minus 3 plus 0 is minus 3, and minus 0 plus 1 is 1, and minus 1 plus 2 is 1. Okay, so it's not quite an echelon form, but we can see we can do 3 row 2 plus row 3. 1, 3, 0. It doesn't affect the top row. It's not going to affect that row. And then we're going to have 0. And 3 plus minus 3 is 0. 3 times 0 plus 1 is 1, and 3 times 0 plus 1 is 1. And right away, you can see that this is going to have, because this is the column R, the R, S, and T column. So we can see from the third equation that t equals 1, that s equals 0, and that r plus 3s equals 1, but since s equals 0, this becomes r equals 1. So in fact, it does, and you could answer the question without actually solving it, because you could say, okay, all three variables are leading, therefore it's going to have a unique solution. It wouldn't matter. You could have more than one solution if it wasn't a basis. So that therefore, W equals 1 plus 2x is in the range of the map. And we found that the vector that did this, the pre-image, was 1, 0, 1, because it's R, S, and T. So this now it's in basis D of the polynomial space. This is the pre-image of of 102, right? So if we want to know what vector was being sent to this vector, this is the 1 plus 2x, but we can also write this as 101 d equals, well, this is 1 times the first vector in the basis, plus 0 times the second vector in the basis, plus 1 times the third vector in the basis. So our map J sends the third thing here was not this, it was x. The third is x, so it's 1 times x. So it sends 1 plus, the image of 1 plus x equals 1 plus 2x. Or you could write it as J of 1 plus x equals 1 plus 2x. Showing you, here's the vector that leads to this vector. So a lot of this is just, there's all this technology for going from maps and matrices and vectors and representations, and you just have to practice this until you it becomes more familiar of translating, between different things. Does this make sense? So, Stephen, what is it's like, I know it takes time to sort of get the big picture or get all the pieces together. Is there something that's bothering you, or that's something that some piece that's sort of dissonant?
I guess if the ends, the map J says 1 plus x, or maps it to 1 plus 2x.
Right.
But in the problem is posed as J mapping a vector R3 to.
Oh, yes. So you're right. Okay, so I jumped the gun. I was okay. So yeah. So this is okay. This is actually. So this was actually. I forgot what the problem was. You're actually right, Jonathan. I mean that that this isn't a standard basis of R3. So this is actually this is okay. This is a different problem. This is if the map was between, this would be solution if map was P2 to P2. But in fact, it is J of 101 in the standard basis equals 1 plus 2x. So this is what's going on. You just had to find the 101 and you were done. I just somehow thought, oh, it must be since it's it's one of these mixed maps, right? It's from column vectors to polynomials. So if you just go along, you can lose track of what you're doing.